All right, so welcome to this lecture. We will mostly continue our discussion on self-adjoint operator. In particular, I give you a reminder. Maybe this. So we were talking about derivative, first and second derivative, and our goal is to compute its adjoint operator. In particular, we want to check whether a first derivative and second derivative are self-adjoint or not, and when they are self-adjoint, when not. Okay. So what we have done so far is that we are considering these absolutely continuous functions, and then we have the domain using this h1, h2, and then we also have integration by parts formula that we have been used extensively, and we will also use today. And now our example or ongoing example is that this operator t, which is partial derivative, and in our convention we have a minus I. There is a reason why I put minus I, that is related to, in a way, a Fourier transform, because if you put minus I in front of that, then when you take Fourier transform, then you only have the Fourier variable. Otherwise, you will have I there. But okay, it's a matter of choice, taste. All right. And then there is this operator. So second derivative is the square of this operator t. So t is squared. That is defined this way written. And we proved a lemma that the image in the of perpendicular is C1, and the image of T2 perpendicular is C1 plus Cx. And yesterday we started to compute the domain of this operator, in particular domain of T star and T square star. All right, so we had few steps, and now let's continue with that. All right. So let us continue with. Oh, sorry. Let U1 is an element of the domain of T, and U2 is an element in the domain of T square. So remember the boundary value of these functions. So remember U one A, and then how to write? Okay, let's just write everything explicitly. So U1A, U1B, these are the boundary values for the element of operator T1, and for T2 is U2A and U2B. But remember, it's a second order of, double derivative. So we also have to specify their first derivatives. So first derivative of U1A and first derivative of, U2A, U2B. So all the boundary value vanishes. Okay, let's write this way. vanishes. So using integration by parts, let me bit uh, abbreviate it today. Maybe I use this abbreviation, integration by parts. Okay. So what we get if we apply integration by parts is u1 with g1. Remember, by inner product we mean in this example L2 inner product, and that's equals to, sorry, u1 prime. I want to with derivative, then u1 g1 prime. There should be a minus. So instead of minus there, I put a minus there, and then there is no minus in the right hand side. Okay, now this equals to u1 is our u1. Remember, where is our g? Here, this g1, g2, we defined yesterday. Here, g1, g2, so their derivative is h1, h2. h1. So if you don't understand u, h, sometimes because my writing in iPad is not good, so please raise your voice. This, and now h1 is nothing but the action of t star on v, or v1 if you want to put. And now we take the other way around. So t u1 v1, and this equals to minus I u1 prime v1. Okay, and similarly we also compute u2 double prime inner product with g2. So again, same game, we put, and then all this integration by parts. So first we apply integration by parts, that gives u2, and then g2 double derivative, which is same as u2, and we know g2 double derivative is nothing but t square star of v2, and then we play the same game, we bring it the other side. So t star u2 v2, and this gives us minus u2 double prime v2. So straightforward computation. So yesterday there was a question, why we considered integration by parts. I hope now it's fairly evident why we did it, because there was as a preparation of this. Okay, now as we have seen that minus I u1 first derivative inner product with v1 minus I times g1, this is 0, and so is u2 double derivative with inner product v2 plus g2. We have just seen. And then what does it tells? It tells that this orthogonality that we have yesterday, V1 minus IG, sorry, 1 G1. This is image of T perpendicular, and same for the other, which means that U2 plus, sorry, V2. V2 plus G2. This is in the image of T2 perpendicular. And let me just remind you, we have also shown that this is that I mentioned also today. This is C1 and this is the C1 plus Cx. So that means those elements are also like these functions. Okay. Maybe better if we write it. Let's write it here again. So this is C1 and this is C1 plus Cx from above lemma. Yeah, we applied lemma. Yes. Okay, now the function, again, let's observe that G1, which was the integration over H1, and the identity, which is just 1, gives X. These are, of course, H1, AB, and G2, 1X. This is in H2, AB. So we can simply conclude that from this that G1 is definitely an element of H1 AB and G2 is an element of H2 AB. Okay, so that means we are almost done, but a slight thing because we have remembered T square star and T star square. So how they are related, let me comment. So far what have we shown? We have shown that what we want to prove, like this is statement of the lemma for T star. So far assertion is for T star. Okay. And now observe that H2 AB, this is domain of T star. Let me just write it square, okay? So it's a T star square of this. And we also have that T star square of acting on V is just minus double derivative of V. Okay. Now, domain of T square star. Okay, I think it's good to have more brackets so that there is no confusion. This is definitely a subset of H2 AB, and since T star square is an restriction of T square star, so by the general properties of adjoint, we have the assertions for both t square star and t star, sorry, other way around, t star square. Okay, and that proves the lemma. In other words, now we know what is the domain of adjoint of first derivative on h1 naught, and what is the domain of the second derivative of this operator, and that is precisely given in this lemma. So the main point is I wanted to show how to get the domain of an adjoint operator. Okay, now why we are doing this? Because as I told, our name of the section is that we want to show that whether it's self-adjoint or not. So to prove something is self-adjoint, what we have to prove that it is symmetric and their domain match. So now we basically look for this closed condition. Okay, so that gives our next lemma. So now we want to show t star equals to t. What this shows, this basically shows that the operator or the first derivative is a closed operator. So that means t is closed. Okay, so let's go for the proof. This proof, again, we will use this integration by parts. Nothing very fancy, but let's see how to progress. I mean, I also wanted to show how to compute things. Okay, so we know this is always true as a matter of fact, that as we discussed, a operator, the adjoint of an operator is always greater or at most equals to this operator. And then we have double adjoint. So then what we have to show actually, to show, the other way around. So we have to show that t star. So that t star is a subset of t. Okay. So usual game, let's put W is domain of T double star. Now we have just shown I write it this way, lemma, that T is smaller or equals to T star. I mean, that's we also discuss in general. Hence, let me write this way, it's more clear than. Lemma, and then we have T star is contained in T star. Yeah. And then what about the element? So W element of domain of T star. We have also seen this is nothing but H1, AB, and T star W equals to minus W. This is also from lemma. We have proven just now. Okay, very good. Now, for any V in the domain of T star, we play the old game. So T star V W minus V T star T star W. This must be 0. Now, what is this side? Oh. So just put the definitions here. Minus I V prime W minus I V. No, I is there. So V minus I W prime. And this is nothing but minus I times V of B W of B minus V of A, complex conjugation, W of A, whole bracket. And this is again our old friend integration by parts. So this is actually a very usual trick. Those who are not familiar, when you want to prove something adjoint with differential operator, if we have no idea what to do, at least the first guess is to do integration by parts, if it is possible. Okay. Okay. Now, since V, I mean the element of this boundary value, let's put VV and VA, elements of domain of T star are arbitrary. That means we can, this can be only true if this condition, this W's are 0. So then WA equals to 0 equals to WB. And thus W is in the domain of T, and this close out proof. Okay, so now we know this is also a closed operator. Very nice. And now we want to prove self-adjoint. In fact, we can prove a bit more. Remember, we had 3 things: symmetric, self-adjoint, and essentially simple adjoint here. So in fact, now okay, let's write it. Why not to write it in terms of equation? I mean, what's written is correct, but since I write in equations, bit symmetric. So now we will see that this is not only self-adjoint, rather this is essentially self-adjoint. Now, to proceed, let me introduce one terminology. And the terminology might not be very surprising, is related to the domain of an operator, because I have at least tried to emphasize repeatedly what is the domain. So now we put a name for a specific domain, and that is something called core. So a domain of an operator. By an operator, I mean linear operator on a Hilbert space on which the operator is symmetric no sorry on which okay, no, let's write this way. Getting complicated. So T is a linear operator on Hilbert space, and we assume that this is symmetric. I want to write domain of T to Hilbert space. And so on this domain, sorry, I'm changing a lot. So T domain of T, which is a dense subset on H, and we assume that this is symmetric. Okay, that means this is the domain on which the operator is symmetric. And if this operator is an essential self-adjoint operator, so domain T is called the core of T if T is essentially self-adjoint. In other words, the domain of an essentially self-adjoint operator is called core of this operator. Okay, it's just instead of telling this whole sentence repeatedly, you use one word, core. So core is the domain of an essential self-adjoint operator. Okay, good. So as I have introduced, so probably you have or you can anticipate what we are going to do. Now we would like to know the core of our operator T. So let's define an operator T naught. This is defined as, so we have the operator T already, and we also introduced the notion of restriction and extension of an operator. And T naught is restriction of this operator. So operator. And when I tell restriction, you will say, restriction where? On a dense domain, let's call it D naught. And what is this guy D naught? D naught is all smooth function in the interval AB, real valued, such that their boundary value vanishes. That means U equals to 0, UB equals to 0. Okay. Now we want to show lemma that D naught is a core sorry for my handwriting, is a core for T. So T T by definition. That means if we take the closure, this is equals to T. Okay. Let's prove it. Proof. So again, let U is an element of domain of T. So far what we have done, we computed the domain of the adjoint, and our main tool or say observation is that integration by parts gives you boundary values. Oh, sorry, there was a question. Is this definition of domain or T? You mean the core? Yeah, domain. So, okay, let me clarify. So we have an unbounded operator T with some domain on a Hilbert space. Okay. And we assume this is a symmetric operator. Okay. So we do not know, we just know that T star equals to T, but we do not know anything about domain. And now, if this operator T is essentially self-adjoint on this domain, then this domain is called core. So to be a core, definitely it has to be a domain, but it satisfies even a strict condition. It is essential self-adjointness. So at this point, is just a domain where the operator is symmetric. Yeah, so it's a not very restrictive. And then we ask, okay, where is this operator essential self-adjoint? So very restrictive things we are now asking. And if this is the domain where the operator T is essentially self-adjoint, then we call this, then we give this domain a specific name, and that is called core. Is it clear? Okay, so thank you for your question. Okay, so where we were? Okay. Yeah. So we use this integration by parts formula. And one of the thing, integration by parts mean is integrable, but isn't circular argument because we prove T is self-adjoint. No, at this point we do not know. Okay, so so this part of definition is independent of this lemma we are proving. So forget about all this lemma. This is just a definition. So this definition tells that, say you have an operator which is symmetric on a particular domain. That's your setup. Okay. And then if you are able to show that this is essentially self-adjoint on this domain, then we will call this domain core. In other words, an unbounded operator core is the domain where an unbounded operator is essentially self-adjoint. Is it clear now? Okay, thank you. But yeah, thanks for your question. Okay, so integration by parts, and as they call integration by parts means it's integrable. So that means L-wall functions are very pivotal in this derivation or proof so far. So our idea, and now you see that where is our core? This core is C infinity, not L1. So, and I think there was tutorial. Hopefully now you are a bit comfortable with C infinity, C1, L1. Okay, so now how can we relate these two worlds, C infinity to L1? Yeah, because not all C infinity functions are L1. So the idea is that, okay, let's try to approximate by C infinity functions to L1, and then we can use the nice results we have proven for L1. Okay, so that's what we are going to do. So let's go. Um, since the derivative is L2 AB, therefore there exists a sequence UN N N from C infinity A B R such that yeah, I need more space, so just want it. Vn can be approximated to U prime in uh, in L2. Okay, now how or what is this element of the sequences? So we define UN function of x is integration from a to x Vn of t dt. So that's more or less like the earlier definition we are using. And now kind of this error term or approximating term. So x minus a b minus a inverse, and from a to b Vn t dt. So I am expecting that at least some of you or maybe all of you have questioned why we are defining this way. This is kind of this epsilon delta definition, yeah? So you put your epsilon and delta such a way that you can satisfy this epsilon delta condition. So there, it has been chosen this way so that we can satisfy what we want to show. And we will see it, okay? Bear with me. So now there is something called Holder inequality. If you know, you know. If you do not know, then just take as a black box. That tells that Vn also converges to Un in L1 AB. It's just a consequence of Holder inequality. Okay, nothing. I mean, it's a very interesting and important inequality, but nothing more is going. I know this is a jump, but please allow me. Okay, now this implies that integration from A to B, B and T dt converges to A to B V prime dt, and by fundamental theorem of calculus, this tells VB VA, which is 0 by this setup we are using. Therefore, T Vn is minus Oh, sorry, just un, because u is t. Un equals to minus vn, we just come from here, plus the other part, plus I b minus a inverse integration from a to b vn t dt. And this converges, as we have just seen above, to I u prime, and which is nothing but tu. But important thing is that everything is in now L2 AB. Now remember, our boundary values are 0. So UA equals to 0. And now let's look at the definition of UN. So for x in the interval AB, UN x, UN x, hopefully is distinguishable, and then U x, this is less than equals to integration. So we are just using this expression of un from above, a to b vn of t minus u first derivative of t dt plus the other term, integration from a to b vn of t dt and modulus. Okay, now observe that Vn converges to u prime in L1. So the right hand side tends to 0 as n goes to infinity. Therefore, un x, hopefully you can distinguish. If you not, just let me know. Nx looks very similar. Maps to, converges to u of x uniformly. So those who are not familiar with uniform convergence, it means that there exists some constant so that all elements of the sequence is bounded by the constant irrespective of this sequence holder like n. On AB, and hence UN, this is really n, converges to U in L2 AB. And this then naturally tells that T naught UN converts to T U N converts to T U in L2 AB. And that gives ends our conclusion. Okay, so then what we have seen, okay, maybe it's good to recap what we have been doing. It was a bit lengthy thing. So let's go back. Yeah, here. So we were considering the first derivative as a unbounded operator on a Hilbert space. And I hope now you are familiar how to define an unbounded operator on a Hilbert space, the domain, and all this issue. We are also interested second derivative because kind of the governing equation in quantum mechanics, Schrödinger equation, which has second derivative, so makes sense we want to study it. And we also define it as an unbounded operator on a Hilbert space. And also by Hilbert space, we mean here L2 Hilbert space. Okay, first we prove that the image of this operator perpendicular is C1, and the image for the other operator T square perpendicular is C1 plus Cx. So this was kind of a technical result that has been used later. Not much of, I would say, I mean, not in terms of, I mean, we haven't gone physics right now, but let's put, this is a technical lemma that's required to prove other thing we are interested. Okay, so then using that, most important thing I would say in this example is that we actually explicitly compute the domain of the adjoint of this operator. And I commented it yesterday, I am still stressing it today. Usually computing concretely the domain of an adjoint operator is impossible. Okay, but these are very nice, simple operators, so we can do it. And there's the computation. So yeah, we have seen yesterday and we finished it today. Okay, so once we know that domain and adjoint, natural question for us is whether it is self-adjoint. And to, in fact, we in this case, we can do even more than self-adjoint. We can go for essential self-adjointness. So to go for that, we also prove that this is a closed operator, which means that T star is T adjoint and adjoint is the operator itself. Okay. Once we have proved that, then we want to prove essential self-adjointness. And in the notion of essential self-adjointness, the domain where the operator is essentially self-adjoint is called core. So this is, I mean, okay, it was the claim that this is the core of the operator. And then we have shown, yes, it is indeed the core of this operator, which basically tells that, okay, if you restrict this operator on a smaller domain, so T was defined in a larger domain than D naught, but you restrict, but still you can recover T by just taking closure. So you see, from T naught to T is you just have to take the closure, nothing more. So that's the closure. So if you take closure, and as you know, the closure of operator is nothing but closure of the graph, right? So that is the thing, and that's ends what we want to. I mean, at least one very concrete example how you compute the domain of an adjoint and how you show some operator is self-adjoint, in this case, essentially self-adjoint. So I give you maybe 1-2 minutes to contemplate, and if you have any questions, because this is really one of the key point where math physics say differ a bit. Yeah, let's put it this way. Because in physics literature, usually self-adjoint means symmetric, and which is not right. Yeah, it's nothing like mathematical sophistication, and sometimes people called, oh, it's the same thing, you just phrasing in a different language. This is nothing about language or sophistication sort of thing. Literally, this concept is much deeper, and that is what required. Otherwise, for an unbounded operator, You can, as we explained yesterday, you cannot just use the notion that operator can be represented as a matrix, and you just use as a matrix to say adjoint and all these things. This is not possible. Yeah. And and you see that this is one of the simplest operator, just first derivative or even second derivative. Even to account these operators, you really need this mathematical sophistication or proper mathematical understanding. And one of the question that some of us is interested, and definitely that is a matter of interest, why this mathematical rigor way is necessary to understand quantum mechanics. Hopefully, this is a very concrete point you can see. So, in quantum mechanics, we will discuss in some detail later. Self-adjoint operator are central object as an observable. So, to be something as a quantum mechanical observable, it has to be self-adjoint operator. Now, how you define actually self-adjoint operator? And I do not know any other way than that for unbounded operator, and even first derivative or second derivative, which are simple operator in some sense. They are right from the beginning unbounded operator. So you quantum mechanics really tells us you have to understand unbounded operator, and you see for unbounded operator how to compute. If you just compute using the knowledge from linear algebra, I actually do not know whether you can get any of this. Okay, so yeah, I give few minutes, questions, comments, discussion. Or even if you are lost, completely lost about all these things, feel free. Okay, I do not see any question right now. Uh, but yeah, please raise your voice, even if you want to share your opinion. Okay, so then let us continue. um, we have seen another approach to address differential operator, and that is using Fourier transform. And when this is possible, this is in some sense much more convenient and less computational heavy than this, because by Fourier transform we have seen that a differential operator transform into a multiplication operator, and then we can also deduce this thing. Yeah, so let me go that approach. So we have already discussed multiplication operator, and in fact the adjoint of a multiplication operator, that's the beginning. Maybe we go back a bit. Here. So the adjoint of a multiplication operator is same, but now you do multiplication with a complex conjugation. So from here is understandable, or it is more or less evident. Maybe another example. So as before, we discussed multiplication operator f, and from the discussion we have seen that multiplication operator by some function f, if is self-adjoint, if and only if f is real valued function almost everywhere. Okay, now use this fact to study Laplacian, because that's what goes to Schrödinger equation, which we will discuss at some detail later. So I think 2 weeks or maybe 1 week before, we have shown that the Laplacian is unitary equivalent to the multiplication operator with this Fourier variable square, right? Now we have just seen that if this function is real valued, then this is self-adjoint, and definitely this is real valued. So this is self-adjoint. Now we have also seen that the domain of m psi square, let me recall, we had it, but it's better to recall now. Yeah, so U is L2 D such that psi square Fourier transform of L2, sorry, U is also L2 RD. And those who are familiar, this space is also called Sobolev space, named after Russian mathematician Sobolev. Okay, that means the domain of this multiplication operator is actually Sobolev space under Fourier transform. And then we can say the Laplacian on the domain as Sobolev space D is a self-adjoint operator. Okay, so then because we have worked hard, or we worked already for multiplication operator, then without going to this more functional analytic approach. I mean, okay, both are functional analytic approach, but in this case, if you know multiplication, then you more or less can deduce, provided you have Fourier transform. Okay, we also discuss about something essential self-adjointness. So let's discuss this in this setting. So okay, we have saw it as a special case, but maybe I give as a result also lemma for an essentially self-adjoint operator the closure is the unique self-adjoint extension. So we have seen a special case of this here. Yeah, the closure is the unique self-adjoint extension. But this is true in general. I'm not going to prove it, but you can find this any standard text. For instance, some of I have mentioned. So let's go for our example. So now we consider again Laplacian, but compactly supported function on D. Okay. Now, what is the domain of its adjoint? So, domain of adjoint of this operator is nothing but functions u L2 RD such that for phi compactly supported functions on RD, this L2 inner product, if phi, triangle phi is bounded. Yeah, so that's the domain. Okay, but this is by Langerel theorem. So we go to now Fourier. Okay, there is a typo. It's not F. This is U. Is nothing but okay, maybe I want to distinguish it a bit later. So this is L2 RD with measure dx. And the blue one is L2 is still RD, but now the measure is d psi by twice pi d. Okay? Usually it's not written explicitly, but it has to be understood. But since we are trying to understand it very clearly, let's do it at least once. Okay. So that means U is in the domain of Laplacian, adjoint of Laplacian, if and only if there exists a function v on L2 Rd such that v minus psi square Fourier transform of u is orthogonal to the Fourier transform of compactly supported function on Rd. Yeah. Okay, but what does this imply? This implies that v equals to nothing but psi square Fourier transform of u. Why? Because the space of compactly supported functions is a dense subset. Okay, right. Of L2 Rd. So that means that you can take every, and no matter any element can be approximated by a compactly supported function. And we have Fourier. How the Fourier works? Because we know that Fourier transform is unitary. Good. Then we can deduce that u is in the domain of adjoint of Laplacian if and only if psi square of Fourier of u is also on L2 Rd. Yeah. In other words, this is same as saying that domain of Laplacian is H2 of Rd. Now, observe, we have just proved that Laplacian on Sobolev space is self-adjoint. So from this and the above deduction, we can show that Laplacian on the space of compactly supported functions is essentially self-adjoint. In other words, this is core of Laplacian. So in a way, this Fourier method is much more simpler than the other method I have shown. But there you are using a different functional space, this functional space of almost continuous function. Here we have L2. So if we have L2, then it's good because then Fourier, we can use Fourier. Okay. But is it clear now how the domain is acting on different things? So it's depending on domain. Sometimes it is self-adjoint. Depending on domain, it is essential self-adjoint. And depending on domain, it might not be self-adjoint at all. So, any questions? Comments? Maybe we all are lost. Let's check. Let's see how much or how many of us is still on screen. Oh, that's fantastic. At least there is one who is not lost. Even better. Now, even better. So, three of the six participants. So, 50% of you are not lost. That's really fantastic. I understand it a bit. It is so abstract and it takes time to digest. I need problem and revision. Yes, that's precisely. And that's why I shall give you one problem in your next homework to show certain operator is self-adjoint or not or something. So you will get at least one opportunity to explicit make your hand dirty. And it is abstract, and I believe most of you are encountering it as first time. This course is not really standard at all. Um, Even I do not know actually whether in Bangladesh anywhere this is taught. All right. So thank you for the three person who are still active and following this lecture. Other three, yeah, may or may not be in front of the screen. Okay. So any questions? Those who are following. I mean, okay, I see your comment. Any other? Unitarity means there exists a unitary operator so that uh, you can write Fourier transform. We discussed it earlier. I can go. In general, unitary means there exists a unitary operator. So you can write A. So unitary operator is U. A equals to U. B. U inverse. So where is Fourier transform? Mm, here. So you see, this is a Fourier transform, and then if you go to Schwarz space, then this is what you have an isometry, and unitary means bijective anisometry. So means that there exists an inverse and is also an isometry. Okay, and Plancherel's theorem tells that Fourier transform is unitary. That's the thing we are using. So does it answer your question? All right. So we have really worked hard. At least you see now how to compute things. You also know the abstract definitions. Now I give you one lemma that is very important uh, for quantum mechanics. Later we will see. Before that, uh, okay, so there is a question. Something I came across yesterday, that the domain of unbounded self-adjoint operator forms a manifold given the operator is dense. If so, will we be discussing this in future lectures? No, because we do not have any plan to discuss differential geometry. So manifold and all these things. Um, so there is a plan to offer a differential geometry course under the ICT PPWF later of this year. But it depends who is going to deliver. So if it is in a mathematics rigor way, then of course we will discuss what is a manifold in a proper way, and that is intended to have a introduction of theory of smooth manifolds and so on. But for this course, we do not have any plan. And in fact, there is no time actually, because as you see, I am skipping a lots of things. But if you have interest, or if you want to talk, we can talk before or after lecture. Yeah, we can discuss about it. All right. So now let me give you a lemma, and we will see why this lemma is interesting shortly. So lemma. So T and S are self-adjoint operators on a Hilbert space. I want to write self-adjoint operator on a Hilbert space. And S is a bounded operator. Okay, I think I will get rid of. Oh, so bounded operator on the Hilbert space. Then there's some T plus S is a self-adjoint operator, and the domain is equals to the domain of T. Furthermore, their sum is essentially self-adjoint operator on a core for T. Okay. Again, I'm not going to prove it, but let's see an example why this is interesting. You can find the proof any standard textbook. For instance, I referred those which I referred. So the example we want to consider is that let V is L infinity real valued L infinity function. And then we cook up the multiplication operator by V, right? We know and how to do multiplication operator. Okay. Then from our earlier discussion, we know that MV is a bounded self-adjoint operator on L2. Yeah, because we have proven these things actually today. Okay, now comes this lemma. Now this lemma and the earlier example we have seen that if we consider the Schrödinger operator, which is Laplacian plus V, by this what is meant is Laplacian plus multiplication operator with V. So we know the result only for Laplacian, right? We do not know, we know the result for this is a bounded, but we do not know the result for this so far. So one approach can be we just follow what we have doing here and then see. But this lemma tells that, oh, you don't need to work that hard. Rather, this lemma tells that this Schrödinger operator is self-adjoint on Sobolev space. Why? Because this tells that the domain will be the domain of T. In this case, T is the Laplacian, and we have seen Laplacian on Sobolev space is self-adjoint. Okay, and what about essential self-adjointness? And this is essential is self-adjoint. Why is the Laplacian essentially self-adjoint? Here in its core is compactly supported function D. So you see, once you know about Laplacian and something about the potential, then you don't need to work for their sum or the Schrödinger operator. Rather, you can just use this lemma and tell, okay, what's going on. We will see how important this is when we will consider simple harmonic oscillator. All right. So now you may wonder, okay, we are considering very specific operator, in particular, differential operator. But life is not all about differential operators. There are many other operators. So what about them? How you compute the adjoint, how the domain, self-adjointness, and so on. And the answer is, as I have told repeatedly, in general, there is no generic prescription to do it. But people has developed over the time some characterizations and conditions from which you can abstractly say something is self-adjoint or not and sort of thing. And this is in a way depending on the problems, yeah, like this theorem applies for this and so on. So of course, I'm really apologize. I do not have time to go through very extensively of that beautiful theory, but let me give you at least two very important criterion for its self-adjointness. So criterion or criteria, because more than one, for self-adjointness. So first theorem, I want to show. So suppose that T is a symmetric operator. Okay. And let Z is a strictly complex number. Complex. Then the following are equivalent. So, okay. Following, the following are equivalent. First one is T is self-adjoint. Second one is T is closed and both T star minus Z and T star minus complex conjugation of Z are injective. Another one is both T minus Z and T minus Z complex conjugate have bounded inverses. I have one more, so I want to write it actually there. I don't want to go to the next page so that everything is same page. Okay. Number 4. Both T minus Z and T minus Z prime are surjective. Okay, so that means that you can prove any of this, then you can go back and forth from any of this. And as you can understand, often one is easier to prove than another one. Again, due to time constraint, I'm not going to prove this very interesting theorem, but you can find it. Any questions, comments about the statement of this theorem? Okay, I do not see. So then give you another theorem. Again, T is a symmetric operator. and Z is strictly complex. So the following are equivalent. Number one, T is essentially self-adjoint. Number two, both adjoint of T minus Z and adjoint of T minus Z complex conjugate are injective. Number three, both T minus Z and T star minus Z have dense range. Okay. So again, for proof, look at the references I have suggested. So instead of going to the proof, let me give you another example where we can apply this or any of this theorem. So example, we consider Laplacian as usual. Okay, not usual, but we are very much interested in Laplacian because that's a kind of a natural choice for quantum mechanics on the domain, which is compactly supported smooth function from 0, 1, and the Hilbert space is, of course, L2, 0, 1. Now, you can just check this is symmetric because integration by parts. Yeah, because you will not get any boundary term because we have a compactly supported function. Now, question is that, is it self-adjoint? And if self-adjoint, then is it essentially self-adjoint? So you can, of course, try what we have done before. Yeah, that's perfectly okay. Or we can try any of these theorems. Yeah. And then, because as you have seen, if you can match any of the condition, then you can immediately say whether they are self-adjoint or not. You don't need to work hard. So again, instead of going that route, let's apply this theorem and see. So what we learned from earlier examples is that we consider some non-zero element of the Hilbert space, which is orthogonal to the range, right? And we have to show that this is strictly complex. So from earlier examples, the knowledge we have is that it is sufficient to um, produce a non-zero element in the Hilbert space that is orthogonal to the range of Laplacian minus z for z strictly complex. Okay, so now let's go on. Let u is a smooth function of the interval 0, 1 and phi is a compactly supported function over the interval 0, 1. Now we do what we do, integration by parts. So u Laplacian minus z phi, this equals to, as we have shown, if you take the other side, u double derivative minus complex conjugate of z u phi. Now, what's the equation form? Sorry, there is a minus here. Yes, because Laplacian has a minus. Okay, that means we can write minus u double derivative z u p. Okay. So then what's what's the equation we have to consider is this. This is the equation. So u double derivative plus z u equals to 0 admits non-trivial solutions. For example, u of x equals to e to the power I z complex conjugate square root x. Yeah, if you put, you will see, you see that it will show up by direct inspection. Okay. Now we use this equation, and then the solutions are orthogonal. So solutions are orthogonal to the range of this operator. And now check. So if this is orthogonal, that means this is not satisfied. And therefore, theorem Eto is not essentially self-adjoint. Okay? So you see that you can use this theorem without working much harder, or with working less. Yeah, so it's an efficiency of this theorem. All right, so now we are more or less end of this discussion of self-adjoint operators. So let me now give you maybe some time. Those who are on screen and following, are there any questions? comments, because that's how we want to end the discussion on self-adjoint operators. So if you have any questions, comments, please feel free to raise your voice. Uh, Otherwise, we will go to the next section. So who is lost? Feel free to give me a text or raise your. I mean, we are only 6 persons, so if you are comfortable, you can directly say, or you can write me in a personal message. Okay, I do not see any questions, comments right now. Hopefully, some of you are in front of screen still. Um, is there anything I can explain more, or if you want to have more explained? No? All right, then let's go to the next section. So the next section is the spectrum. Um, to motivate what we mean by spectrum, I hope all of you could recall the notion of eigenvalues. Is there anyone who is not familiar with the notion of eigenvalue? So maybe I pose this question. So again, let's go to linear algebra. So linear algebra. So we have the vector space CD, and we consider some linear operator. Let's call it L on this vector space. So V vector space to vector space. Since linear okay, thank you for your comment. So then we have the notion of eigenvalue is that L acting of an element of the vector space if produce something scalar like lambda times V, and that is called eigenvalue, right? Okay. Now our target is to get an analog or generalization of this eigenvalue for our setup, in particular, unbounded operator. Yeah. So, who thinks for unbounded operator we can define eigenvalue exactly this way? Let's check how many of us are still on screen. So do you think we can use the same idea to define eigenvalue of an unbounded operator? I mean, what can be, is there any problem if we want to use this for unbounded operators? Okay, I do not see any immediate response. Also, the time is not that long, so maybe this time, instead of going to poll, let me introduce some terminology. And next lecture, we will see why these things are interesting and how they are related, what we know and what we do not know. So, allow me to introduce some definitions. Definition. So, as usual, T is a linear operator on Hilbert space. That's our setup. However, what we are going to do is actually applicable for any closed linear operator. Okay, so post linear operator. Okay, so the first thing, I want to use L. I mean, T is not a problem, but so lambda is a complex number. This belongs to the resolvent set which usually is denoted by rho L of the operator L if the operator L minus lambda with identity has a bounded inverse defined on H. So since it has a bounded inverse, that means defined on H means that defined everywhere on H. Okay, not the usual sense. I mean, not the sense of a linear operator on a on a dense subspace. Mm, so maybe good to be very explicit here. So inverse. So let me just write lambda, but always to be understood in the sense of lambda with identity. Okay, defined everywhere. Okay, so lambda belongs to the resolvent set of the operator if the operator L minus lambda has a bounded inverse defined everywhere on the Hilbert space. And maybe continue. And is called, and this is called the resolvent of L at lambda and denoted by R lambda L. Okay. Now, once we have defined the resolvent set or resolvent and an operator, then this set sigma of L, which is the complement of resolvent. So C complement of resolvent set is called the spectrum of the operator L. Okay. So in linear algebra, by spectrum, you means a collection of all eigenvalues, and how this definition is related to that, or is it a generalization, we will see later. But today, just let me introduce these words. Okay. Now, the spectrum can be divided in a finer classification, or I mean, finer way. So the first thing we are going to define is this sigma p, p for point spectrum. So this is the set of lambda belongs to C such that the kernel of the operator is not trivial. This is called the point spectrum of L. We call an element of the point spectrum of L an eigenvalue. So now I think you see where you know from linear algebra sits into. The dimension of the null space L minus lambda is called multiplicity. Multiplicity and any non-zero element in this space is called an eigenvector of L at lambda. Okay, and our time is over. There are still a few things, but anyway. So I thank all of you for attending today's lecture. Any questions, comments, or any generic thing? So I'm here for few more minutes if you want to talk about, discuss something. Uh, Next lecture, we will discuss the spectrum, some notions. I mean, now you already have seen how eigenvalue pops up, um, but why we need to take this approach, we haven't discussed. So we will discuss thing, and we will also. So there are something more, and this will show up, and I shall give you at least one two example, like again, that you will see the difference between linear algebra and functional analysis in the sense of a spectrum. And once that's over, we will go the heart of this course, this spectral theory. Yes, I apologize once again for not uploading, but I shall upload it tonight. The reason of not uploading last night is that when I was going through the lecture notes, I couldn't really figure out which lecture goes to where because I was not putting lecture number. Maybe that was not a good idea. So I need some time, but I shall do it tonight. Or if I cannot, I will just upload everything so that you know everything is there. Welcome. I hope you have enjoyed this session and the core of functional analytic argument. Okay, yeah. So if I can figure out, I will just upload whole PDF. So then, but yeah, tonight, hopefully, I shall do it. So that's the plan for spectrum. And then once the spectrum with some examples is done, then we will go to the spectral theory or a spectral theorem. And that goes actually the question we raised the first lecture, how we define function of an operator. Okay. So hopefully um, next after next lecture, you will see how to define function of an operator. And then you will also see why these things, I mean, I hope you get some idea why these things are important, but you will see more why these terminologies and the hard works you have been going through are important. So any further questions, comments? Okay, if not, then thank you once again to all of you who have attended this lecture. I hope to see you all next week. Bye.